Hello, I'm Charles Cantliner.
Hi, I'm Janani Ramakrishnan, and we're going to talk about Mosfet modeling in analog circuits.
In this project, we will sweep each terminal of the Mosfet to determine its internal parameters. This is done for both the INFET and the PFET. The first experiment is the gate sweep. For this experiment, we will keep the source voltage at 0 and the drain voltage at 2.4 volts. This is the linear graph of channel current versus the gate voltage for the NMOS and PMOS respectively. This plot is not the easiest to interpolate data from. As you can see, taking a linear regression of the square root of channel current is much easier. From the listed equations we found a slope-intercept form for the square root of the channel current versus gate voltage, where we can pull out the parameters for threshold voltage in terms of K and kappa, the threshold channel current, and the equation relating K and kappa. As you can also see, the simulation data is close but not exactly correct. The previous graph highlighted the above threshold region by taking the square root of channel current. In order to focus on the subthreshold region, we will take the log of channel current versus gate voltage. Using the slope-intercept technique and the subthreshold equations listed above, we can find the I0 and the subthreshold kappa. As you can also see from the simulations, near the y-axis of the dotted blue line, there is some diode leakage in the experimental where we don't have that in the simulation data. Finally, for the INFET, we have the plot of the transconductance over current versus current. To find this, we use the MATLAB diff operator. Moving on to the PFET gate sweep, for the above threshold region, we use very similar equations and techniques to find the same parameters but for the PFET. As you can see from the simulation and the experimental data, the PFET is a flipped version of the INFET. This is the subthreshold graph for the PFET, where we extracted the data for I0 and the subthreshold kappa. Once again, we can see the diode leakage, but for the PFET it is near the right side of the graph. This is the graph of the transconductance over current versus current for the PFET. Once again, we can see the similarities with the INFET plot. If you look at the minimum of this graph, you can see the noise produced in the experimental data.
The second experiment is the analysis of source voltage versus channel current. For this experiment, we'll keep the gate voltage and drain voltage at 2.4 volts and the bulk voltage at 0 volts. This is the linear graph of channel current versus source voltage for both the NMOS and the PMOS. As Charles explained earlier, taking a linear regression does not adequately provide the required results. Based off the given equations, we plot the square root of channel current versus source voltage to obtain values for the threshold voltage in terms of K and kappa and an equation relating K and kappa. The simulation results are not perfect, but they closely agree with the experimental data. We plot the log of channel current versus source voltage to obtain the analysis in the subthreshold region for the NFET. Using the above equations and expressing them in the slope-intercept form, we obtain values for the terminal voltage. The measured value and actual value were comparable. This shows the above threshold voltage for the PFET. Using the equations for the PFET, we extract values for the threshold voltage in terms of K and kappa and an equation relating K and kappa, similar to the NFET. Once again, we use the plot of log of channel current versus source voltage to obtain a value for the terminal voltage for the PFET. And this value was also comparable to the actual value of terminal voltage. We obtained two equations for K and kappa from gate sweep and source sweep. On solving these system of equations, we can get a value for K and kappa. The third experiment was the analysis of drain voltage versus channel current. Here, the gate was kept at 0.4 volts and the source and the bulk were kept at 0 volts. The set of equations expressed in slope-intercept form give us the following graph for channel current versus drain voltage. The graph describes the ohmic and saturation regime. From the slope, the early voltage is calculated, and the graph's intercept provides a value for ID sat. Once again, the simulation results and the experimental data are quite close, but they're not perfect. A similar analysis is conducted on the PFET, and a value for early voltage and ID sat is extracted.